Part of this unit is also related to logical effort, but it is slightly different from what we were doing before. Here it is related to choosing the number of stages. So before, in the previous case, the number of stages was fixed, meaning we have the logic and we want to determine the sizes for the intermediate stages. In this case, n itself is not fixed. Suppose we have a situation where n is not fixed. How can we choose such that the delay is minimum? Okay, so that is the approximately that is what we are trying to do here, and it's a special case. We are only going to work with a chain of inverters. So a chain of successively larger inverters. So for example, if we go back to this board here, I have my block. Okay, it's driving a output, say for example, a relatively large output load. Okay, maybe something like my output capacitance is say 100 units. Okay, and the input capacitance is relatively small, say 1 unit. And this is generally the case when you're driving external loads. So for example, if you're driving a primary output, it's going through the pin, the load is going to be very high. So we will never generally drive this, because if you look at this example, the suppose we have our final output is just an inverter. Okay, and I want to calculate the delay for this particular structure, and we have our method of logical effort. Everything is fixed, we can just calculate the delay directly. So what will we get for the delay equal to G into H plus P. Very simple in this case, because G is just one inverter, 1. H is 100, right? 100 by 1 plus P is 1. So the delay is going to be 101 tau, 101 units of delay. It's very large. So generally in this case, what we do is between the input and output, we insert a buffer. Okay, a buffer is nothing but a series of inverters. Okay, and these are going to somehow reduce the delay. So let us just see one example of, say I have put one more inverter. Okay, and now we can use the method of logical effort. We know n equal to 2, because I have one gate here, I have one gate here, and the output is 100, that is fixed. So by the method of logical effort, two stages, each stage effort should be square root of 100, which is 10. So 10 plus 10, that is 20, plus 1 plus 1. So in this case, okay, the delay is going to be how much? Delay equal to 20, which is two stages, 10 each stage, plus 2 equal to 22 tau, which is a very good number compared to 101 tau. 101 tau is very large number. I don't want such a big delay. So by just inserting one inverter, I have reduced it from 101 tau just down to 22 tau. Now again, we are very greedy people. Can I go better? Can I keep getting lower and lower? Will it go all the way down to 0 tau? That would be very nice. So thankfully for that, we have another method where we don't have to do a trial and error. We can use some simple arithmetic modifications to find out what is the value. So in this case, this is the problem that is being set up. The delay D, okay, we have chosen n equal to 2, but that is not necessary. We don't know what it is. We know what is the value of capital F, because in this case, it is just a chain of inverters. So your G1, G2, G3 all are 1. So capital F is just going to be H, because G1, G2, G3 all are 1. It's a chain of inverters. There's no branching. So B is also 1. So capital F is just going to be output capacitance, which is what I am required to drive, divided by input capacitance. So that is F. and this part is just the parasitic delay. And if I want to minimize this, what is the value? This two n's here, it's a little confusing. All are the same, it's just small n, this should be small n. And if I want to solve this for n, I just have to differentiate with respect to n, and I get this equation. Unfortunately, we don't want to solve it by hand. We can solve it numerically using inverter parasitic delay equal to 1, and gives us this very simple nice equation. Capital F to power 1 by n is 3.5. This is the equation that you have to remember if you want to design a inverter chain. Okay, so in this equation it's not always going to be constant, the n, because our f keeps changing. Suppose I have a load which is 20, then I calculate what is the value of n for f equal to 20. I'll get some number. If I have a load which is 100, then I have to recalculate for f equal to 100 what is the value of n. And in all of these cases, for simplicity, we're just going to assume that the input capacitance is 1 unit. That can be changed. You can give whatever you want. That what we can get is f. And from that and this equation, we will get the value for n. And one thing to remember is that n, what does it mean physically? It is the number of stages. So 3.783 stages doesn't mean anything. If you get in any numerical n equal to 3.783, then you have to round it up or down to the closest number, and that will be the number of stages which will give you the best possible delay. So let us just try one numerical, relatively simple. A control unit generates a signal from a unit-sized inverter. Okay, the signal must drive unit-sized load in each bit slice of a 64-bit data path. So the fan out is 64, and each branch has the same unit-sized load. And we can add inverters. Polarity doesn't matter, which means that you can add odd or an even number of inverters. But how many should we add to reduce the delay? That is the question. So we'll just try to do this. Okay, so I have a unit sized inverter 1, and this is driving 64 bits of a same unit sized paths. So 1, 2, 3, etc. Why do we need this 64? We need this to calculate the fan out or H. So this we can replace with inverter driving a load of 64, and this is our problem. And like the example we saw, we don't want to directly let the inverter drive such a large load. We want to insert a chain of inverters. Okay, so what we need to do is, how many inverters should be there in that chain? So we start with 1. Okay, and this is our inverter chain, and this is our output port, and we want to see what is the, so in this case n equal to log 64 divided by log 3.59. This is the n that is going to satisfy our least delay requirement. So if you solve for this, you should get about 3.25, and since it's a number of stages, we are going to round it off to 3, which means that our inverter chain, including this inverter, this is also part of the chain, is having 3 stages, which means successively larger inverters, and final inverter is driving the output, and we want the sizes for this and this. Now we can use the method of logical effort. We have three stages, okay, 1, 2, 3. To get least delay, the each stage effort GIHI should be equal to cube root of f, which is 64. So that should be equal to 4. And once you have this, then it becomes relatively easy. Each one is reducing by that much. So 16 times 4 is 64. So this should be 16 and this should be 4. And once we have these numbers, we can get the delay also. Delay D equal to 3 into each of these. GIHI is 4. So that is 12 plus each of these is parasitic capacitance 1, that is 3, equal to 15 tau. This is the delay for your inverter chain, and this is the design of the inverter chain. So this is the second application of the method with logical effort, and this is generally used to size our inverter chains for least delay. Okay, so with this we will end this second unit, first part of second unit at least, and the second part we will look at alternate logic families, etc. This slide just provides a summary of the method of logical effort. Okay, so we will stop here.